This is EE300 Linear Circuit Analysis 2, Module 3, Video 2, Frequency Response. In this video, we'll review our previous results. We'll look at the concept of and execution of the frequency response idea, and then we'll have a summary and some previews. So let's review the sinusoidal steady state. We've got a linear circuit. Here it's just presented abstractly with an input V1 of t and an output V2 of t. And the transfer function, the zero state response transfer function between those two, is the ratio of the output in the S domain, V2 of S, to the input in the S domain, V1 of S. And what we discovered so far is that when a sinusoid is the input to the linear circuit, the output's going to be a sinusoid of the very same frequency, but the amplitude's going to be scaled by the circuit gain at that frequency, and the gain's going to be a function of frequency. And then the angle's going to have the circuit phase added to it at that the circuit phase at that frequency added to it. So if you put in cap V sub A, amplitude V sub A, cosine omega sub A t plus phi sub A, it's got a frequency omega sub A, an amplitude V sub A, and a phase phi sub A. Out comes magnitude h of j omega sub A times V sub A, cos omega sub A t plus phi sub A, plus angle h of j sub omega sub A. There's a new amplitude, which is the original amplitude V sub A scaled, multiplicatively scaled, by the gain at omega A, magnitude h of j omega A. And the phase has been added, even though we say added to, but h of j omega A can be negative, and we'll see it's negative often. So the new phase is phi sub A plus the angle of h of j sub omega A, which actually may be less than the original phase in the sum if angle h of j omega A is negative. So let's look at an example of that. Here's our RC circuit. Familiar parameters: 1 k ohm resistor, 1 microfarad capacitor. Looking at the output across the capacitor, H of S is 1 over RC over S plus 1 over RC, with R and C is given. Then RC is 10 to the minus 3, so 1 over RC is 1,000. So the transfer function is 1,000 over S plus 1,000. So when the input is cos 100t, then we want magnitude of h of j100 times cos 100t plus angle of hj100. So we need h of j100, so you just plug in j100 wherever s is in h of s. And then since 100 is a lot less than 1,000, it's a factor of 10. So it's not exactly less. It's, the denominator, if you take 1,000 out, then you've got 1 in the numerator, and you've got 1 plus j.1 in the denominator. And that's almost 1. I mean, it's got a little bit of an angle, and it's also got a little bit of a magnitude that's less than 1, but it's still 1. So it's almost 1. So we say that the output is 1 times cos 100t. So the output is in the bottom panel, the input's in the upper panel, and the output looks just like the input. Now for the case when the input is 1,000t, cos 1,000t. Now we have h of j 1,000, and so 1,000 over j 1,000 plus 1,000, which is the same as 1 over 1 plus j. 1 is just 1, but 1 plus j can be thought as a complex number, root 2 e to the j pi over 4. It's got a real part of 1, an imaginary part of 1, so it's got a magnitude, which is root 2, and an angle, which is pi over 4, but that's in the denominator, so the overall value is 1 over root 2 for a magnitude, and minus pi over 4, since you have the angle of the numerator minus the angle of the denominator. So when we put this into V2 of t, we get 1 over root 2 times cos 1,000t minus 45 degrees. And when we look at the graph there, we can see the amplitude of 1 over root 2, which is 0.707. And then you can see the phase shift. That is, it's been delayed because it has this angle of minus 45 degrees there. It's actually delayed by 1/8 of a cycle, since there's 8 45-degree chunks in 360 degrees. So you can see it's a quarter way through the cycle of the sinusoid there. It starts a quarter cycle later, peaks at, we'd have to figure out what that time is where it peaks, but it'd be 1/8 of the period, and the period's 2 pi over 1,000. If we have a high frequency now, the frequency is cosine 10 to the 4th, the sinusoid is 10 to the 4th t. So now we need h of j 10 to the 4th, and now 10 to the 4th is bigger than 1,000. So we factor out 1,000, we factor out 10 to the 4th, and we get 1/10, but now we get in the denominator a minus j. The j 10 to the 4th term dominates in the denominator, and then you take the j into the numerator to get minus j, and you take 10 to the fourth into 1,000 to get 10 to the minus 1. So minus j is a complex number e to the minus j pi over 2. It's got a real part of 0 and an imaginary part of minus 1, so we can think that it was a negative 90-degree angle there. So the output is 0.1 cosine 10 to the 4 t, the same frequency, but now it's got a phase shift of 90 degrees, a quarter of a cycle. And we look at the output in the lower panel on the right, you can see that it's smaller. It's been scaled by a factor of 0.1. It's a tenth as big as the input. And then it's got a shift of 90 degrees, which turns the cosine wave into a sine wave. So this is basically what happens when you put sinusoids into circuits. Sometimes they come out with no amplitude, sometimes they come out bigger, sometimes we haven't seen that case yet, but sometimes they will. And sometimes they come out with a scale factor of 1 over root 2, and sometimes they come out substantially smaller with a phase, and you see the angles can be sometimes 0, they can be sometimes minus 45 degrees, sometimes minus 9 degrees. Well, rather than calculating this for every possible value, which would be a real pain, why don't we determine this for all values? We've got a formula for h of s. We can put in j omega and then figure out the magnitude, called the magnitude of the frequency response. We're going to call this function h of j omega the frequency response. So we'll call magnitude of h of j omega the frequency response magnitude, or the gain. And we'll call angle of h of j omega either the frequency response angle or the phase angle or the phase. They all get used, so you have to deal with that. And we usually present these graphically rather than as formulas. So we'll plot the magnitude of h of j omega versus omega, and we'll plot the angle of h of j omega versus omega. H of j omega is a complex number, so it would either have real and imaginary parts, but those don't show up in the sinusoidal steady state formula as useful. What shows up as useful is the magnitude and angle. So we plot the magnitude versus omega and the angle versus omega. So here's our circuit. We've got 1,000 over s plus 1,000. We plug in j omega to get 1,000 over j omega plus 1,000. We rewrite this, doing the usual, putting the imaginary part to the right of the plus sign. So, and we've also factored out 1,000 from both numerator and denominator. So it's 1 over 1 plus j times omega over 1,000. So now you can see why things happen when omega is smaller than 1,000, where you can sort of ignore the imaginary part when it's much smaller. And when it's close to 1,000, you get the 1 over root 2 and the 45 degrees. And when it's a lot bigger, you get it gets smaller and smaller because omega's in the denominator there. So the magnitude of h of j omega then is 1 over the square root of the real part squared plus the imaginary part squared in the denominator. So that's 1 over square root of 1 plus quantity 1 plus omega over 1,000 all squared. And we can plot this, and here's what it looks like. When omega is a small number, back over here, we can see that it's very small. When omega is very small, we get a gain that's close to 1. When omega is 1, we get a gain that's about 0.707. Exactly 0.707. And as omega gets bigger, we see it roll off and keep rolling off here. And these are, notice on the abscissa here, that these are in thousands. So this is omega scaled by 1,000. So here's 1,000 radians per second, 5,000 radians a second, and 10,000 radians a second. And you can see that the gain gets smaller, and it's going to keep getting smaller if we do this for a larger and larger omega. So the phase angle, we do the same thing. We've got the same formula, 1 over 1 plus j omega over 1,000. And now it's the angle of the numerator, which is 1, minus the angle of the denominator, which is omega over 1,000. The angle of the denominator is omega over 1,000 because it's the arctangent of the imaginary part over the real part. There was no imaginary part here, so this should not say arctan of 1. This should say arctan of 0, since the imaginary part was 0 here. That's a bug. So this term is going to go to 0, and we're going to be left with minus arctan of omega over 1,000. And we know what the arctangent looks like for positive angles, positive arguments. It looks linear near the origin, and then it gets more and it gets bigger and bigger until it maxes out at about 90 degrees. So it's got this shape like the arctangent shape, to be actual. So it's going to, as omega gets bigger and bigger, it's going to go more towards 90 degrees. Here we see when omega is 1,000 radians a second, we get exactly minus 45 degrees, and it gets smaller and smaller with smaller and smaller omega until you get to the origin where you have a 0 degree phase shift. Again, this arctan 1 is a bug. It should be arctan of 0 since the imaginary part of the numerator is 0. So here's our total picture here. Here's our circuit. We can see the network function 1,000 over s plus 1,000, the transfer function. It's got a pole at minus 1,000. And over here, we've drawn this now with a more, or instead of pointing out the 1,000 point here, we've got 0, 2,000, 4,000, etc. And here's our magnitude response in the upper panel. Here's our gain, our phase angle response in the lower panel. Same curves, just different labeling on the horizontal axis here. And now we've got this. Now we can say, well, what do we do with a different frequency? Here's our magnitude and angle again. What if we put in 2,000 radians per second cosine? Well, we can just read the magnitude and phase off the angle. We don't have to go back to our formula anymore. We don't have to look at our formula again unless, we get numbers out here and we don't know how to deal with that, and we'll see how to deal with that in the near future. So we can read the 2,000 radian per second point. We go on the horizontal axis and find 2,000 per second. Radians per second on both the magnitude and angle, and we look at those and we say, oh, look, in the magnitude, it's somewhere between 0.4 and 0.5. Let's call it 0.45. And it's in the angle curve, it's somewhere, these are in 15 degree increments here, so it's a little bit more negative than 60 degrees. Let's say minus 62, because that's the 75, minus 75 down there. That tick, that's minus 62. So that's probably going to be pretty close. So 0.45 times 10 is 4.5. So the output would be 4.5 cos 2000t minus 62 degree volts. And we could have done this for 8,000 radians a second. We could have done it for 6,000. We could have done it for 3,500. I mean, now we can do this for any possible choice of frequency we want to. And that's the point, that you can see this behavior that as we increase the frequency, the amplitude of the output sine wave is going to get smaller and smaller as the frequency gets higher. And the phase angle is going to get more and more negative until it maxes out at about 90 degrees. And we'll talk more about that next time, how to characterize this in terms of thinking of it as a filter where it has a pass band down here at low frequencies and it has a stop band greater than certain frequencies, and we just have to define what those, where those bands exist and where we want to start those. So to summarize and give a preview, the frequency response captures h of j omega for any omega. That's h of s evaluated at s equals j omega. For any omega, there's a gain term, magnitude h of j omega. There's a phase term, angle h of j omega, and we plot each of those separately versus omega. And then you can read the sinusoidal steady state gain and angle directly from those. So you can do sinusoidal steady state. If somebody gives you a graph of the frequency response, magnitude and angle, you can compute sinusoidal steady states, and you will be asked to do so. So what we'll look at next are first order circuits. I mean, we've already had one first order circuit, and that's going to be our prototypical low pass filter. But we'll also have high pass filters, and we'll have filters where there's sort of a shelving effect. And we'll talk about the differences between different kinds of filters. We can put a low pass and a high pass together to get a wide band second order circuit. But we'll also look at narrow band circuits for an RLC circuit where the damping ratio is between 0 and 1 and getting close to 0, and you get this very narrow band kind of behavior. And that's what we're going to look at next time. So this has been Module 3, Video 2, Frequency Response of EE300 Linear Circuit Analysis 2.